I mean, I'll say a little bit about it, I think. Hi.
So,
How am I? Yeah. What was that?
How long have you been playing pool?
Oh, you mean historically?
You seem
Yeah.
to be pretty good at it.
Oh, I used to be good at it. When I was an undergrad, I played a lot, and I won some school pool thing. But yeah, it's been a while. Yeah, that was not up to my old self. Okay, should we start? Okay, great. So I'm super excited to keep going. I don't know. I had a really fun time last night. I feel like a strong. Or last night. I meant to say yesterday. Also last night. Yeah. No, but there's this. It's a nice reception to everything. So I'm going to continue to try to kind of play it by ear of somewhere between the lectures that I would have often give for like a statistics course and something that's more tailored for this crowd. And so again, we can go off script. So if people have things they want to see or questions they want to ask, I'll just kind of go with it. So the three main topics that I really would kind of plan on trying to get through would be to talk about hypothesis testing, to talk about how you do confidence intervals and exclusions, and then to talk a little bit about sort of statistical modeling itself, because everything I've talked about so far is sort of like someone gives you a statistical model, and I want to talk a little bit about how you actually make the statistical models. That's something I usually focus on a lot when I give the talk to experimentalists, because in some sense they don't need to know about all the details for the limit setting and all the theory for hypothesis testing and things like that. What they really need to know is how to describe the analysis that they're doing in some statistical way and make the statistical model. That's like the important goal for an experimentalist, and then you kind of can plug it into some fairly generic tools for setting limits and discovery and things like that. So I'll go over that just a little bit, and then so that's sort of three topics that are each probably roughly half a lecture. Well, maybe some might go a little bit faster, and then the rest of the time I'm hoping to try to reserve for just going on to whatever it is that we would like to talk about. So last time we ended with this James Stein estimator, where I tried to blow your mind with this strange estimator for this was, say, for a Gaussian, where you're trying to figure out what the mean of the Gaussian is, and you could just take the mean of your cloud of points and move towards the origin, and which seems very strange, and as a physicist has all sorts of problems because it's not invariant to changing like the units, right? And it's also not invariant to changing the like a translationally invariant, depends on what you call the origin. So as a physicist, you would hate this. However, this has a smaller mean squared error. Well, that was the thing that we showed last time, and this was then one of the points that I was making is that before we talked about the Crammer-Rao bound that said that unbiased estimators, their variance has to be bigger than some number, which was related to Fisher information. And in this case, we're not talking about variance. We're talking about mean squared error, which has a combination of bias and variance. And by putting these coefficients of 1 in front of each of these, you're specifying some sort of weighting about how much you care about these two things. If you would have put a gargantuan coefficient in front of the bias, then you would have paid a huge penalty for any bias, and that would have, in the limit, taken you to something like the maximum likelihood estimator and back to the unbiased case in the Crammer-Rao bound. But if this is what you care about, then you can do better. But who says that this is what you care about, right? You need to think hard. So that's one of the main messages, is that no one's telling you what it is that you're trying to optimize. You need to figure out what it is your goal is. So mean squared error is just some kind of ad hoc mixture between bias and variance. And in general, there's this kind of trade-off between the two. Okay. Now, this part is something I want to talk about a little bit. There's a lot on that slide, and it's probably kind of hard to read, so maybe I'll zoom in on some of it. Is this going to work? Yeah. Okay. Look at that. This statistical decision theory is a nice framework for thinking about these problems. And what you sort of have a few main players. So first, you think about a space theta, which is the states of nature. Okay, which could be like the parameters of your theory, or like if one theory, the null hypothesis or the alternate hypothesis or something like that. X are the possible observations that you make, and A is the space of actions that could be taken upon seeing seeing the observation. Okay, so then you have some statistical model f of x given theta. Okay, so that's saying if you told me what the parameters of my theory are, what do I expect the distribution for the observables to look like? Pi of theta is a prior that some of these things will make use of. And then you bring in the idea of a decision rule delta, okay? And it's a map from the space of observations to the space of actions, okay? And that can be like, I see the LHC data, and I claim discovery of a new particle. Or I see LHC data, and I don't claim discovery of a new particle. The space of actions can also be things like your estimate of the mass of a particle. I see the data, and my action is, is a real valued number, which is my estimate for the quantity. So A might have the space of actions might be all sorts of different things. It could also be I look to see what happens at run 2 of the LHC, and I decide to build the ILC or 100 TeV collider or something like that, right? And I think it's important for us to think about those kinds of examples. So then there's the loss function, which is a map from both the space of what the states of nature are and the actions that were taken to the real line, and so that's called the loss function. And it's basically saying, if I say my action was claim a discovery, but the true state of nature was that the Higgs doesn't exist or something, then I would have made a big mistake, and I need to assign a value to that, like how big of a mistake did I make? And the loss function is encoding how big of a mistake that is. It would also have, for instance, I claim a discovery and the Higgs is real. I get $1 million or something, right? So you can think about the loss function in lots of different ways. Okay, and then you have the risk. Okay, and the risk depends on both the states of nature and your decision rule delta. Okay, and what it's defined as is just what is the expected value of the loss function. Okay, so what you imagine doing is you pick some true value of theta, some parameter point. You imagine generating a bunch of data, doing an experiment over and over again, right? That's the expectation you're taking. And for each one of those experiments, you imagine what the data is, and then you apply the decision rule and you take some action, right? So this risk, is sort of this, is saying the expected value of that loss function, but it's expectation with respect to the data, okay? And it explicitly depends on the true value, the true value of the parameters, okay? So you can evaluate the risk for, if you give me a certain decision rule, like a procedure that I'm going to apply, that if that's fixed, I assume the Higgs is not real, I can calculate my risk. I assume the Higgs is real, I can calculate my risk, but I don't know if the Higgs is real or not, right? So like, what do I do, right? And that's a problem. Okay, so now there's this thing that comes in when we talked about the James Stein estimator. The loss function was the mean squared error, okay, and the risk here was just calculating the expected value of the mean squared error. So when I made this plot, wherever it is, this is basically, this should really be the average value of that. So this is the risk as a function of the true unknown, okay, here the theta is fixed. I'm just changing. Sorry, bad example. Okay. Anyways, I'm calculating the risk there, but now, what do I want to say here? All right, so then we talked about there's this idea of a decision rule you can have two different approaches, like the James-Stein estimator and the maximum likelihood estimator. Those are two decision rules in this language, and I can compare them. Okay, and you say that a decision rule delta star here dominates another decision rule delta, if and only if the risk of delta star is smaller than or equal to the risk of delta for all values of theta, and it's a strict inequality for some value of theta. Okay, so in this case, what it would say, the statement about the James-Stein is that the mean squared error is always smaller. The expected mean squared error is always smaller than it is for the maximum likelihood estimator. So that's why the James-Stein estimator dominates the maximum likelihood estimator if you care about mean squared error. Okay. Now, there's also this idea that's basically the same idea. A decision rule is admissible if and only if no other decision rule dominates it. Otherwise, it's inadmissible. Okay, and that can just be of the decision rules that you know about and are considering. Okay. Now, that's great. That's basically what we had talked about before. But again, you have this problem that you don't know what the true value of the parameters are. So what do you do? So there's something else that you can do, and this is where the prior comes in. I can bring in a prior, and it's basically weighting all the different options of what the true state of nature is, and then you can imagine an expectation over both of those. So this Bayes risk is you're taking the expectation with respect to the prior, where you're going, averaging over all the states of nature, you're weighting them appropriately according to your prior, and then for each of them, you have the risk for that value. Okay, so it's sort of a double integral. It has the integral over the prior and the parameters, and then the integral over the statistical model and the data. And this is kind of nice because now you can sort of like, if you had a prior, what you thought the states of nature were, this thing doesn't have any more. You can just consider different decision rules and say which one's better. You don't have to take into account all the possible states of nature. So this is a nice way to sort of make decisions. Okay, and what's interesting here is that this is a nice rational way to make decisions. And if you're the one that's paying the cost, if you're wrong, then it seems kind of nice that it's your prior, right? And it's also a different way you can think of the prior, not necessarily as a degree of belief, but you can also just think of it as operationally something that you need for weighting the different possibilities, right? So it's kind of a semantic distinction, but you can do it. And now then these are just some things that are kind of philosophical, but nice to have in the back of your mind. Is that you can also do the expectation. So there's sort of three kinds of expectations. I can take the expectation over the data, the expectation over both the data and the prior, and the parameters, and I can take the expectation over just the prior. So this thing right here, which is called the expected loss, you're taking the expectation. It's hard to read this again. Let me zoom in. So the expected loss. Let me zoom in because it's you have. So there you have your loss function that depends on whatever your decision rule is, and whatever the parameters are, and you're taking an expectation. And now here, this is actually a posterior probability. So you're saying based on the observed data that I have. So this whole thing is conditional on the observed data that you have. What is my posterior on what the true states of nature are? And then I'm going to average out my loss that way. Okay. So this thing is totally conditional on the data you have. You don't think about other experiments that I could have done and their outcomes. You're just like, this is the information I have in front of me. How should I proceed? Okay, and yeah.
Sorry, a super basic question.
Yeah.
What exactly are you doing with the subscript in this case?
Yeah, this E of this part right here, it just means that when I take the, when I do an expectation, so E of, in this case, pi of theta given x of whatever, just means that I'm taking the integral of pi of theta, given x d theta of, whatever. That's what it means.
So instead of just having that, like normally just put a 1 there, I guess. But in this case, you're taking that.
No, I mean, whenever you do the expectations, you need some like a kind of some measure, some probability measure. So like the other one that's there at the beginning is an expectation with respect to f of x given theta, of the loss or whatever, right? And that's equal to the integral, dx of f of x given theta of the loss of x and whatever. is it? Delta of x and the theta. Is that right? I think so.
So it's a PDF.
Yeah. So this thing right here is just whatever the PDF is that you're using when you take the. That's what that one means. Okay. All right. So okay now, so that's a lot of I'm just defining a bunch of things, but the main thing I'm trying to get at is that those different kinds of expectations they have very different flavor, right? I mean, this one is I have data in hand. What should I do, right? The other one is sort of like before I do the experiment, I don't even need any data. I'm just saying like, what is my risk? What is the expected value of the loss in this sense? I hate this term expected loss because expected with respect to what? It's expected with respect to that thing. So that's the more important part. But now there are a few follow-up results, which is the reason I mention it because this gets thrown around in the frequentist Bayesian debate by people that are somewhat knowledgeable, but it's also widely misused statement. So a lot of people will say, actually I'll even show you, I'm going to zoom ahead real quick, an instance of this being stated. We'll get back to this later. Admissible, Bayes, blah, blah. And people say something like, they don't usually use the word admissible, but they're just like, isn't every optimal analysis Bayesian? And what they're usually referring to is this theorem. Every admissible procedure is Bayesian, and every Bayesian procedure is admissible. Okay, so those sound like super powerful statements. Like, why would you not be Bayesian, right? So let me go back quickly to the kind of fine print in that. And he also says, written separately because neither is quite right. Okay, he's a statistician. He knows what the right statement is, but he's so let me go back to it again and get the. Where are we? Nope. Sorry, I've lost track of where I am. Yeah, okay. Here we go. Almost there. Okay, so the statements are basically, under some, okay, so this idea of, a delta prime, whatever, one of these decision rules is called a generalized Bayes rule if it minimizes this thing, okay? And then it says under mild conditions, every admissible rule is a generalized Bayes rule, okay? So that's what he's saying, right? It's like every admissible rule is a generalized Bayes rule, in bold here, with respect to some prior, okay? Not your prior, some prior, right? So it doesn't mean like if you're Bayesian, you're great with your own prior. It just means like I can rewrite these things in a way that are Bayesian, but you have to back calculate what the prior is that makes that work. So it's not your prior, okay? So to me this is, I mean, maybe it's, I don't know if I'm losing people or it's too abstract, but this is this is often, this thing is misused a lot, and but it's still interesting because we can end up doing this thing where we back calculate priors when we don't think of it in this way. So for instance, when we're frequentists and we talk about discovering the Higgs, we're not using priors. But we decide to either discover, claim discovery or not. So we're taking an action. We have a decision rule that's claiming discovery or not, but it's not being based on anything with a prior. But if I want, I could think of it as like it's optimal and it's a good thing to do and back calculate what prior that corresponds to. So there's sort of an implicit prior in our actions when we establish the 5 sigma discovery rule. So I'll show that explicitly a little bit later. Okay. And then there's this other point, which is essentially the one that he's saying, is that if you are if you do something Bayesian and you have your own prior, that approach that you do is virtually always admissible. Okay, but that's not kind of too surprising in the sense that if you're weighting things with respect to your own prior, then like it's not too surprising that a Bayesian procedure would be admissible. So anyway, so this one probably is worth like looking at and thinking on your own time if you're interested, but just because it's a lot to chew on. But the main thing is that there's a lot in this one slide, but I think it's a great way of resolving a lot of issues. So if you're curious about Bayesian and frequentists, I would just invite you to spend some time and digest this on your own. Yeah.
Sorry, could you just repeat what you mean with proper?
Oh, yeah. So, okay. So, I need chalk again. So we know that if this is some parameter theta, and you have some prior here, pi of theta, you have the condition that the integral d theta of pi of theta equals 1, right? Because it's a probability density function. So this is a proper prior. Okay, you can have you can consider quote priors that don't satisfy this condition. So things like 1 over theta or something that diverges in some way. Also, a uniform prior, if theta is unbounded, is it would have to go to 0, right? So it doesn't really work as a prior. If anything finite would not integrate to 1. However, those improper priors sometimes lead to totally valid posterior distributions. So there's a lot of times that people use improper priors because the posterior that comes out is fine, but you can't really think of that improper prior as a normal, PDF.
But a data distribution would count as a proper prior.
A data, well, I mean, it's a good. I mean, a data distribution is a good PDF of the data. So, but it's for data. So, I mean, usually we use prior kind of on the idea of parameters. So, so I don't know how to parse that then. Yeah. Oh. Oh, you said delta.
Oh, yeah, sorry.
Delta. Data. Yeah. Okay. Okay. Yeah. that was interesting. Okay. The other thing that I'm not going to spend time on, but it came up yesterday. We mentioned this Almonds Theorem or whatever. I'll just mention a little bit, and then we'll kind of get out of Bayes frequentist land. Is that so? This is what came up. So there's a nice blog article that's by Scott Aronson, who many of you might know. He does a lot of quantum information stuff and is a deep thinker. Anyway, so he wrote this nice article about common knowledge and Almonds Theorem. And basically, this is what referred to before. So now imagine that you've got two agents, call them Alice and Bob, with common knowledge. They basically know about, in our context, like all the experiments that have been done and blah, 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 blah. And they believe that each other are rational, okay, which is, a good little bit of idealism here. But then this is the part, and with the same prior probability distribution over the states of the world. So the statement for Ahman's theorem is they come with the same prior, okay, and then basically the starting point is that Alice and Bob might have had totally different experiences. So that when they come to meet each other for the first time, their posterior distributions can be totally different, okay. But then they get to chat and figure out what happened. And after after that whole procedure is done, basically what Ahman's theorem says, and this gave him a Nobel Prize, was that at the end, the rational agents with common priors can never agree to disagree about anything. It's basically just saying that at the end of the day, their posteriors should be the same. And so the way that we talked about it yesterday, we talked about different, can you have different priors and something like that. So this is what we were referring to. I think we said it kind of wrong yesterday, where it depends. I mean, they can have, when they first start to have the discussion, they're in different places, right? So that at that point, their state of belief is different, okay? But that's really a posterior of a common prior and different experiences in life, But I think, schematically, the way that I would maybe write this is going to make it seem like, woo, that's close. A bit of a buzzkill is that imagine that I have, posterior probability for Alice of theta given x. That's defined as the likelihood function of Alice or maybe I won't write. It's the likelihood, but I'll use the same way we talked about it before. The probability of x given theta for Alice. Okay, so whatever experience she had, the likelihood function for her, then a prior probability for theta, which is common to both, divided by some normalization. And then there's the same thing for Bob, right? P Bob x theta prior of theta over some different normalization, okay, normalization Alice, normalization Bob. But whenever they get to talk to each other, what does that mean? I mean, basically, at the end, they're going to have, prior probability of Alice, and Bob of theta given x. And if it's common knowledge, it basically just means they both get to have these pieces, right? So, it's going to be probability of A, x given theta times probability of B of x given theta, and then they're common prior. So, and both of them are going to have the same equation. So it's not, in that sense, it's not a very exciting result. This makes it look like their two experiences can be treated independently and just multiplied, right? And maybe that's not the case. Maybe it's something more complicated, but that's what Almonds Theorem is like, the more thorough version of that, where you're not assuming that it just is a product of two things, but allows people to have overlapping experiences and stuff like that. So it gets more complicated, but in the simple picture where it's just, this is common knowledge, this is common prior, no kidding, they're going to agree, right? So and then he goes on to say, okay, well, now we have a puzzle because hardly any disagreements in the history of the world have ever looked like that, so what gives? And so he goes through a few different, the first one is basically humans aren't rational, but okay, whatever, forget about that. Let's imagine that we're physicists and we know what we're doing, we're rational. And then the second one is this part, is like the other obvious one, is you could reject the assumption of common priors. I think that's a pretty reasonable thing to reject. But then he goes on, and I'm not going to talk about it all, but it's pretty interesting what follows there, is basically there's this argument that people raise, which is like, okay, well, why do you have a different prior than me? And in some sense, life experiences, but if you sort of elevate yourself to the level that I need to imagine that I could have been born in your shoes and you could have been born in my shoes and whatever, then you symmetrize everything. Sure, okay, but that's just not, so if this is not my picture of how we actually work as humans and collaborate. Right now we're arguing over resources and stuff. We're not all trying to get along and imagine each other in each other's shoes. So if we could do that, then yes, fine. We would all be ideal humans and we'd have a common prior. But if it's not that way, then people are going to have different priors, and this theorem does not apply. So, okay. Enough about that. Anyone want to?
You know why they actually won the Nobel Prize?
I think the going beyond this kind of simple thing where the two just factorize, and you want to do something where it required some you had to do some kind of manipulations to show that all partitions of blah 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 give you that, but in Scott's article he's like, well, it's one of these things that sounds profound, but then here's a 3-line proof for it kind of. So I don't know enough about it, to be honest. Okay. All right. So that's that. So I'm going to move to hypothesis testing. Okay. So the starting point that I'm going to do is just thinking about, I think, what at least in particle physics type stuff, what's the simplest way of thinking about it is that I have some background process. I'm just counting the number of collisions in my detector, and say in my background process I expect 100 events to happen from a particular type of interaction for the amount of data that I collected. It's going to fluctuate according to, say, a Poisson distribution. It's going to be, it looks roughly like a Gaussian with the width of 10. And now, and then I can imagine a different, that's going to be my null or background only hypothesis. And then I can assume okay, well, what if there is a new kind of particle around? There's more kinds of interactions happening. Let's say they don't quantum mechanically, interfere. So it's just I can decoherently add them together. So I have some additional source of events that I would expect to happen. So this dotted line is what my prediction is under the alternate hypothesis of the signal plus background, right? Now, so these are the two distributions for the two different scenarios, expected number of events, and now I need to decide whether or not to accept or reject the background only hypothesis. So I get some data, right? Bloop, here comes my data, and now I need to make that choice, right? So then the question is, how do I make that choice? So usually the setup, and this was also kind of, it seems so simple and like it's been there forever, but a lot of this stuff, happened kind of at the turn of the century, not the century, but last one, so it's not all that old, this way of thinking about things. And so it's so this is the way that Nyman and Pearson formulated the problem. So they're going to think of basically you have the null and the alternate, and then it's like the kind of typical table that you've seen, like guilty, not guilty, and is the actual state of nature, and then a verdict of guilty or verdict of not guilty is your decision. So in this case, it's the null is true or the alternate is true, and then I choose to accept or reject the null are the actions that I take. Okay, and so then you can either be right on the diagonal here, or the other diagonal you make two different types of errors. So in the case that, for instance, the standard model is true, but I claim the discovery of some new particle, that would be a type 1 error, and the other one where there is new physics, but I don't claim a discovery, that's a type 2 error. Okay. And then you assign, then you can refer to the probabilities of making those kinds of errors. So the rate of type 1 error, the probability of making a type 1 error is usually denoted alpha. Rate of type 2 error is denoted beta. And 1 minus beta means that if there is new physics and I claim a discovery, I did the right thing. So that's the power. Okay, so that's sitting here. Okay. All right. Now, So at this point, everything looks symmetrical, right? But the approach that Nyman and Pearson took was to treat the two hypotheses asymmetrically. And so you say, I'm going to think of the null hypothesis as special, and I'm going to try to control the rate of type 1 error. So the rate at which I incorrectly reject my null hypothesis. Okay? So now what happens, you have these two different things going on, and now I have a constraint, and then you can think of it in kind of like Lagrange multiplier-y way. Okay? And then our goal is to, under this constraint, to maximize the power. Okay, to claim discoveries as much as possible when they're right, and control the rate at which I make false discoveries. Okay, so that's the setup. So in one dimension, it's with this kind of setup, it's pretty trivial. Like clearly this direction is good, right? So all I need to do is figure out how far out to go on this tail, so that the probability under this black curve, which is sort of this little red area, is the probability, the rate of type 1 error that I'm willing to accept. And in particle physics, we use 5 sigma, which is that invisibly small probability, which is 5 sigma corresponds to 2.8 times 10 to the minus 7 probability of incorrectly rejecting the null. Okay, like claiming new physics when it's not actually there. Okay, so it's a very, very small probability. It's totally conventional. 5 sigma, just made up. We as a field get to decide what our tolerance for the rate of type 1 error is. Okay, and it's just by convention that we've used 5 sigma. Later on, I can talk about the look elsewhere effect, which is related to why that convention's there. But okay. Yeah, so I mean, in all of this, it's like, there's no like you're making mistakes, right? You're just describing everything statistically, and it's not allowing for you to just be wrong about the description. So the reason that the reason that 5 sigma was there early on was because people were afraid that we didn't really understand how to, we didn't really know how to deal with systematic effects. Even if we knew they were there, like statistically, we didn't know how to incorporate them. And then separately, there was the fact that we're looking in lots of places, especially back in the particle zoo days when people were discovering mesons and stuff all over the place. They were looking at tons and tons of plots, and they didn't want to claim a bunch of false discoveries, so they just cranked up the value, but it's totally ad hoc. There was some kind of back of the envelope calculation about how many plots you're looking at, but beyond that, it was not. Okay. Now, in that example that I showed, that one-dimensional picture where you're just counting, it's very easy. But what if my data is, say, two-dimensional, and let's say I just, for the sake of experiment, I do the experiment, I just have one observation. Okay, so this is the space of all the data, and imagine the red and the blue points correspond to the null and the alternate hypotheses. Okay, and the scatter of points is the same in these 3 plots. So now what I need to do is I need to figure out a region in the data space so that when it falls, like, say, in here, I'm going to accept the alternate, and reject the null, or here, right? So now let's imagine that all 3 of these have the same rate of type 1 error, right? So now my goal is to figure out, well, which one of them has the most power, right? Does that make sense? That's the setup. And it seems like, well, I could just compare these. And a lot of times, like when you try to optimize an analysis, a lot of people make cuts on variables, and they're doing something that looks like this, and they're basically just changing the values of these to try to, optimize the thing, right? But there's no reason it needs to look like a box. It could be some weird shape. And so now the question is there a way that we can find out what the optimal way to make that decision? What is the optimal boundary, or that's called the acceptance region, that's going to have the right rate of type 1 error and maximize the power? So that's the question. And maybe it's obvious to you, or maybe it's like not at all obvious, right? So, yes. Sorry, say it again. Yeah, sure. This is the distribution for the null hypothesis. This is yeah, that's right. Yeah, no. So you don't get any choice over what the black lines look like. That's a property of your experiment and nature, right? So what you do get to control is what you call the acceptance region. And in this picture for 5 sigma, if the data falls anywhere in here, you're going to accept the null, and if it falls over here, you're going to reject the null. And that decision property, that decision rule has the right property that the rate of type 1 error is what you want. And now you actually need some data, and the data is going to sit on one or the other side of that blue line. Okay. All right. So it turns out that so this is basically what we said before about this is what I was getting at just a second ago with this plot. It would be nice to figure out what is the optimal region. So there is an answer to that question. So the setup here is I'm going to call W. W is going to be the region so that if the data falls in there, we accept the null. Okay, and these are just the statements that I said before. The probability the data doesn't fall in the acceptance region, given that the null is true, is this rate of type 1 error alpha. Okay, so the statement is that the optimal thing to do is a contour of the likelihood ratio. Okay, so H0 and H1 are 2 fixed hypotheses. They don't have any free parameters in this situation. X is whatever it's the data, right? So this is a real valued function over the space of what's possibly very high dimensional data, right? And then you're just going to put a contour on that, and you're going to adjust the contour level until it gets the right rate of type 1 error. Okay, so that's the statement, and here's the proof for it, which is nice. So we're going to prove it by considering, we're going to assume that it's true and consider a variation. Okay, so here is a contour of the likelihood ratio. We've adjusted the contour level so that it has the right rate of type 1 error. And now we're going to consider some variation about it. This variation also has to have the right rate of type 1 error. I can't consider any variation. I need the probability under the null here to equal the probability under the null there, or it doesn't have the right size. So that's the constraint that we need. And then I know that for all the stuff out here, it's on the wrong side of the likelihood ratio. So I know for all these points in the blue that the likelihood ratio is less than that contour value, that contour level. And on the other side, I know it's greater, right? And so then once I have, this is a statement about the likelihood ratio for the pieces, the 2 different pieces, and then because I know that because I put the 2 pieces together, and I can, it's a likelihood ratio, and I know what's going on for the null. I know that it has to be equal for the null. So then I put the 2 together, and I can prove that this variation has less power. Okay. So it's a very simple variational argument. Okay, so that's the Nyman-Pearson lemma, and this is the reason why likelihood ratios are powerful and important, and you see them all the time. Okay, in this case of simple hypothesis testing, it's the best you can do. Okay, now we went back to talking about statistical, decision theory. We can think about it in the same way, and I'll just go quickly through this. Is that I can think about now my action to claim a discovery or not. Is this decision rule, and then this, I'm going to kind of flip through this, but basically these few slides from Richard Lockhart just go through the Nyman-Pearson lemma and prove, but they do it from the statistical decision theory point of view, and basically the risk that the loss is basically, you say, give a value of 1 if you're wrong and 0 if you're right. So if you're right, you didn't make a mistake, so there's no loss, and if you're wrong, you get penalized. Okay, and then the risk that you end up is just being the two different types of mistakes that you can make. Okay, and the probabilities for them. And then you can work out through some Lagrange multiplier, and what you get is that the solution to that has the value lambda for that Lagrange multiplier, and then you can end up interpreting lambda over 1 plus lambda as the prior probability that you put on the null. Okay, so basically you get to the same decision as the Nyman-Pearson lemma, but in the statistical decision language. And if you want, you can think of this. You see the title is implied priors, as you can say. This is a way of basically interpreting the 5 sigma discovery requirement in terms of what our implicit prior is on the null being right. Okay, so for 5 sigmas, you'd expect you're saying that I think that the null is probably right. I think I don't think that new physics is very likely. Okay, so I'm gonna stop for a second. Yeah.
Is there an optimal trade-off between type 1 and type 2 error?
Well, you need to provide this loss function, right? And there's the trade-off is also. You need to know kind of the penalty associated to the two kinds of things. So you can imagine if we claim the discovery of a new particle and it turns out that we're wrong, that's super embarrassing for the field, and Congress cuts all our funding. And but if we're if we don't claim the discovery of some new physics because it's marginal or whatever, but it turns out that it's real, people, you missed it, but I understand, minus 2 points for you, but that you might consider that to be very asymmetric. But at that level, it's still 2 different values of the loss. It doesn't tell you kind of how to trade the 2 different types of errors because you don't know which reality you're in. So to be able to do the optimal trade-off, the extra thing you need is the prior that gives you the weight between the 2. And that's what all of that. If you go through those equations, is exactly what the set of equations. You can interpret it in lots of different ways, but it's exactly the relationship between your priors on the things and the loss function for the different kinds of mistakes. Okay. All right. Anything else? Should I do something silly to wake you up? Okay. All right. You ready? Okay. All right. Okay. Stupid human tricks. Okay. Now, I'm working hard. The hardest working man in Tazi. Yeah. Okay. What's that? Okay. So I wanted to touch base to something. This is something very new. Okay. It's just this term is new. This somehow has been implicit in what we've been doing as physicists for decades, but it's not been talked about in this way that I'm going to talk about it. And this is the way that it definitely is in the last year and a half or so is the way that I've started thinking about things, and a lot becomes very clear in this way. So I'm going to talk about a topic called likelihood-free inference. Okay. So let's go back to, in everything I've shown, the probability model is just given to you, right? So let's think about where do we get it, and at least in a kind of particle physics language. So at first, we have quantum field theory, we do perturbation theory, we get Feynman diagrams, we stick that into computer codes, do scattering processes and integrate over phase space, and they generate a bunch of examples, a bunch of Monte Carlo simulations of what the collisions might look like at the particle level. Then we do parton showers and hadronization, and then those particles run through the detector. And the detector is complicated, right? There's magnetic fields, there's iron, there's wires, there's all sorts of stuff. And these simulations that can take, something like 20 minutes per collision, even though the real collisions are happening 40 million times a second, these collisions are very complicated, and they have particles flying around and scattering off nuclei and disassociating and there's all sorts of microphysics going on. And it's very complicated in the way that, just like the first part happened, the particle level, you're using Monte Carlo. Monte Carlo is sampling a distribution, and as you know, it's also a way of doing an integration, right? So you should always think of Monte Carlo secretly as an integral, right? Okay, it's like So the Monte Carlo is just doing integral over phase space. And now I also have a Monte Carlo code that's following a pion, smacking into a nucleus, exciting it, it decays, whatever, something Brimstrahlungs, all that stuff happens. That's basically a gargantuan integral over all the microphysics of the detector, right? But I mean a really, really big integral, right? So we do that. Then the space of the data is something very high dimensional, like 100 million dimensional, because it has the electronic readouts of all the sensors. Then we run algorithms to try to reconstruct it to get back to a simple picture to say here's an electron or here's a photon or something like that, right? Now, so that's roughly the chain that we do, and so we have all of this coded up into some computer code, and that's our Monte Carlo simulation, or let's just call it simulation, right? And I can use it to generate me a bunch of examples of what the data could look like. And conceptually, that thing is probability of the data given the theory and the detector description, right? So I'm saying here, conceptually, say the detector simulation is probability of detector response given the particles. The implementation is this huge Monte Carlo integration over the microphysics. The consequences of that is that if you give me an event at the LHC, like say this one, it looks like this, I can't evaluate what the likelihood of this event is, right? I can generate a bunch of examples, but if you gave me that event to calculate the likelihood, I would have to integrate over all possible, all possible things that could have happened inside, right? All these hidden variables that are going, not in the quantum mechanical sense, but latent variables that I would have to integrate over. So you can't give me an event, and you can give me an event, but I can't tell you what the likelihood of that is. And that's, of course, a problem, because everything I was just showing you was Nyman-Pearson lemma. It's wonderful, but that only works if you can evaluate the likelihoods and take the likelihood ratio. So in a situation like this where you have a complicated detector simulation, you can't evaluate the likelihood ratio. Okay, so this motivates a new class of algorithms for what's called likelihood-free inference, which only require the ability to generate samples from the simulation in the forward mode. Okay, is that fine what I mean by that? Okay, so now what do we usually do? I mean, we do physics all the time. We have simulations. So what we usually do is we have the complicated detector simulation, and then we pick one good variable, right? I mean, how many of you have spent some time trying to come up with a great discriminating variable, that's going to make some new physics be good? So in some cases, like the Higgs to 4 leptons, the invariant mass is a very obvious, good, physically motivated variable that has a lot of separation power. But we don't know what the distribution of this thing looks like after the detector response. So what we do is we generate a whole bunch of samples and we make histograms, right? And that histogram is an approximation of the actual likelihood function. If we have enough simulations, it's a very good approximation, and then we continue on. But at some point, we made this transition from the real theory to this surrogate model for what's going on, which is a histogram, okay? And that's fine. I'm not criticizing it. It's just in these cases, in one dimension, it works fine if you have enough, Monte Carlo simulation. But this does not scale if the data is high dimensional, right? I can't fill histograms in 10 dimensions, effectively, right? So that means that I can't, practically try to do a likelihood ratio if I want to represent the data in this high dimensional way. And for some things, like when you have, if you want to do spin CP properties or particles, you have lots of angles and you need all that information, right? There's lots of examples where you need a high dimensional version of the data to really get everything. And you can't come up with one nice variable to, encapsulate it all. So some of the stuff that we've been doing recently is sort of trying to address this problem. But a lot of this has been done for a long time. And this is why part of the reason why physicists use machine learning algorithms. And I know a lot of theorists hate machine learning algorithms. They're usually described in a very poor way, like neurons and brains and lines, or like trees and all this stuff that sounds very ad hoc. And you're like, I don't. Why should I care about any of this stuff? So I'm going to describe machine learning in a totally different language as applied calculus of variations. Okay. So going back to this picture I showed before, I have a bunch of red dots and blue dots, right? I run my simulation. I get a bunch of examples from my null, a bunch of examples from my alternate. Those are the red and blue dots here. And what I would like to do, is, if I knew the distributions, I would have a likelihood ratio. And so imagine that these blue and red curves were actually contours of the true likelihood ratio, right? they could be. The problem is I don't know how to evaluate that, right? So machine learning is basically trying to approximate those ratios, that likelihood ratio function. And here's how it works, is that you can imagine that that what let's say I'm going to provide, have a different goal for a second. What I want is a function that's going to map signal events, say they're the red ones, the blue ones, to y, the target value y equals 1, and background events to y equals 0. Okay, so ideally, if I give it a signal event, it will return 1. If I give a background event, it will return 0. But because these distributions overlap, there's no way it's going to be able to do that perfectly, right? Okay, so now since it can't be perfect, I need to describe what my goal is. What am I trying to achieve? And so I'm going to provide one of these loss functions. Okay, so my loss function is going to be so this is an expectation over data that came from the null hypothesis. Okay, so this is written not as samples but as an integral equation with actual distribution, right? So so if the data came from my null hypothesis, 0 is what I would like it to return. S of x is going to be the function that it's actually, the actual function that the machine learner is providing. It's going to give me some number. The difference between those things squared. Okay, that's going to be my loss function. And then plus another piece when the data comes from the alternate hypothesis, and that now the target is 1 squared. So this is just the squared loss function, some L2 norm. Okay, and this is a functional of the function s, right? So now it's calculus of variations time. I want to find the function s which minimizes this loss, right? So now hopefully all of this is like super clear first principles stuff, right? Now this integral is what I would want to do if I knew the actual PDF, but if I can't evaluate this, but it's approximated by the sum over all of my examples, where half of the examples I came from the null hypothesis and half of the examples I came from the alternate hypothesis, and each one of them has a label that tells me where they came from, right? And so here you don't see the p's in there because the samples are already proportional to the p's, right? You have the samples xi are being drawn proportional to these distributions, so that's why you don't see a probability there. Okay, so the generator in the process of simulating encoded this in where the samples are, right? Here you have more samples where the probability density is high, so there's more contributions in that sum. Yeah.
What precisely is S in this case?
S is the so in the thing that I talked about before, the likelihood ratio was a function of the data, is a real valued function of the data, right? So S is another one of those, but it could be. Here it could be any function. It's any function, real valued function of the data x.
And it's supposed to be a function of all the different variables involved?
Sure. Yeah, in principle you just stick every.
Variables and takes it into one basically.
That's right. It's just a map from the space of the data to the real line. Okay. But it's a functional. The loss is a functional of s, and I'm trying to find the function s that minimizes this loss. Okay. So now, so if you do that. In the pure calculus version where you actually know what these distributions are, it's very easy calculus of variations problem to show that the optimal s is this function. Okay, and it's not you can see it very easily if it's the data point is clearly from the alternate, then this probability is 1, this probability is 0, this probability is 1, 1 over 1 is 1, and if it's very clearly the null hypothesis, this probability is 0, and it works. And if it's anything in the middle, you get something else. So this is called the regression function, whatever. It's just some function. But the important part is that it's 1-to-1 with the likelihood ratio. It's easy to see these two things are 1-to-1 with each other. So that means that the contours of these functions are exactly the same. And so in the point of view of the Lyman-Pearson lemma, where I'm trying to find the optimal decision boundary, all I had to do is find the right contour. So it's a different it's a different contour level, but it's the same contour. Does that make sense? So what happened here is that we were able to rewrite the Nyman-Pearson lemma in a way that only requires generating a bunch of examples. So when I generate a bunch of examples, I can approximate this loss function. Okay, and now the question is how do this is the ultimate goal that minimizes that loss function. Now how do you do a lot of variation, like if you've maybe done variational quantum mechanics at some point, something like that. Usually what you do is you come up with some very highly parameterized set of possibilities, and then you try to minimize with respect to that parameterized set of possibilities, right? So that's what machine learning is. A neural network is some class of functions S with a whole bunch of parameters, which are what's going on in the neurons or whatever. And you're just optimizing it to find what function in that class of functions minimizes the loss. Okay, so that's why I call it applied calculus variations. And what's great about this is that you can do everything just with a simulator. Okay, yeah.
Something confusing me about this. Is it important that the number of red and blue points be equal, or could they be arbitrary?
Yeah, if you want, you can include another factor in front of these, which is basically how many events from the null and how many from the alternate, and then you get some factors in here. But the resulting function is still 1-to-1 with the likelihood ratio. So yeah, so if they're not balanced sets, then there's factors that don't make any difference in the end. Yeah. Yeah. So the question is, so here's a plot from that's actually here's an example of this S function. You take a bunch of events from the background only. You evaluate the S function, and this is the distribution of it. Excuse me. A bunch of events from the signal only. That's the distribution of that. You see these in some experimental papers sometimes. The problem for theorists is like, I don't know what your function S is, so what do I do? And I agree. That's definitely one of the problems about the way that we use machine learning now. It can be trivially solved if the experiments just provide that function, right? So and that's totally possible technically. You can just save these neural nets and boosted decision trees and things as some function that you have to evaluate. And okay, yes, you lose insight into what's going on and things like that. But if you don't think of the variable in the sense of like an invariant mass or some kinematic variable, if instead you think of it as I'm trying to learn the likelihood ratio and I know what the distribution for the events under the null is, and I know what the distribution of the events under the alternate is because I wrote the Monte Carlo and I trust the experimentalist to have a good simulation of the detector, then this is the thing you're computing. End of story. You don't have like you don't have some kinematic picture of what's going on, but that would be true even if you could do it exactly. Like if you gave me the matrix elements, I can just compute this ratio directly, forgetting about the detector response. I also don't know how to interpret that other than it's the ratio of the probabilities, right? Right. So the question now is that if you don't know what this function is, then you're relying on the accuracy of the simulation, and so because the simulation is what you use to learn this function S. That's true, but the thing is that there's two very important points here. One is that let's say it's a variable that I do understand, then the axis, the variable is the axis, not the distribution, right? So this axis could be the invariant mass. And how do I build the distribution of the invariant mass? I run my simulation, and I run it through the detector simulation. I build histograms. So the problem with the simulation is they are independent of what the variable I'm plotting is, right? So I can just think of S as some observable quantity that I can calculate, right? So the problem with the simulation is totally independent of the fact that S is a neural network or something. That also applies equally well to invariant masses and transverse masses and all these kinds of other variables. I wasn't planning on it in these. I mean, you can talk about all of these things. In my mind, it's all, it's applied calculus of variations. There are all different algorithms for how to do it. There's a bunch of details. They'll continue to improve. There will be all sorts of, I can tell you how they work, but it's not, not a lot to it. There is a nice connection between neural networks and one of Hilbert's problems, okay. All right. Right. Okay. And then the last thing that I'll say, this is a little bit of just since we're on it, I'll show it. But this is some work that I did very recently. So, but it also gives you a feel for the power of what can happen. So this S of X that we just talked about was what it is when you have two discrete hypotheses, signal and background, right? But what about scenarios where I have a parametrized theory, right, with free parameters that I want to move around? Well, I can think of S of x here implicitly depended on the null and the alternate, right? I could just make it explicit and say it's S of x that depends on the null and the alternate, right? And now, instead of, then it's the same equation, but instead of thinking of the null and the alternate as two discrete hypotheses, I just replace it with theta, where it's now a free parameter, right? And so if I can learn this function, S that depends on both the observed data and two different values for the parameter points, it will learn this function, which is 1-to-1 with the likelihood ratio that I would want. So it's all the same equation, just rewriting it. But if you, in that case, instead of having a normal neural network or something that just takes in the data and gives you back a real number, you need to learn what I call a parametrized classifier that takes in the real data and the two parameter points that you want to compare. And when the function it will have learned is 1-to-1 with the likelihood ratio that you would like to use. So then if you can learn this object, then you can do all sorts of likelihood-based inference using all the information in the data. So high-dimensional versions of the data, but even in this likelihood-free setting. So the thing that you would get, for instance, is like, whatever this is notation that we haven't really talked about. This is called a test statistic. But basically, here's the likelihood ratio. It's a product over a bunch of events. Here, I'm imagining that I actually could evaluate the likelihood ratio for the high-dimensional thing. This is my target. This is what I would love to be able to do. But in this likelihood-free inference setting, I can't do that because this involves a detector simulation. And so there's a theorem that I have that shows that likelihood ratio is equal to this likelihood ratio, which is the probabilities still under theta naught and theta 1, but you're considering the one-dimensional projection of the data. So this is a particular dimensionality reduction map from the high-dimensional data to one dimension that preserves all the information. So you have an equality here, and so to do it, you need to have a neural network or something that learns this function, and then you need to run your simulator and figure out what the distribution of that function looks like. And if you can do that, you can rewrite the high-dimensional likelihood ratio in a practical way just by using your simulator. And so this is all super new. There's a paper, for, the archive number for it or whatever. But but I'm pretty I think this is pretty promising for whatever stuff in the future. So, okay. So that was the end of that part. So I'll stop if people have questions. Yeah. Yeah. So what's interesting about it is that normally a classifier, all you need to do is stick in the data, and then you get back a number. And the parametrized classifier is a little tricky because so here it's this S of x given theta naught and theta 1. So x, the data, I know that's observed, but how do I evaluate this because I don't know what theta naught and theta 1 are, right? And so that was the thing that was like I was stuck on for a while, and then I realized that I can postpone the evaluation of this function until later. Later on, I'm actually going to be doing inference, right? And so what I can do is I can imagine in this likelihood ratio, I keep theta 1 constant, okay? Later on, when I'm actually doing my likelihood fit and I'm doing the inference, I'm testing explicit values of theta. And at that point, I know what the value of theta is. So if I fix theta 1 to any arbitrary value, it's fixed. And I use it both to build the distribution, and I use it as the value of the, when I'm evaluating the S here. And then as I'm scanning around in my likelihood scan theta naught in the numerator, I know what the value of theta naught is to build the distribution and to evaluate theta naught there. So, it's the same values of theta naught and theta 1 in both places. So at the time that you are actually doing the inference, you know what x, theta naught, and theta 1 are, and you can evaluate the likelihood ratio. And once you do that, then it's just the, at that point, so let's imagine that this is the likelihood of theta naught in the numerator, right? So I'll just minus log likelihood of theta naught in the numerator. I picked some random value of theta 1. So this axis here is theta naught. I also picked some random value of theta 1. Okay, like here, this is okay. Say this was theta 1. So the denominator has that value, right? And so when I take the log likelihood ratio, if I instead I think it as this theta 1, then this this is my 0 line, right? Because that's where the likelihood ratio is 1 and the log of 1 is 0, okay? And so I pick a random value of theta 1. It's arbitrary. I can scan theta naught. And then if I want now, I can find the minimum. This is theta hat, the maximum likelihood estimator. And then I think about, levels, from here up by some amount. And these are going to be so this is going to be my best fit value, and these are going to be my error bars. So it's all totally all doable. Okay. All right. Okay, so this stuff is very new and fresh and kind of forward looking, but I wanted to get into some of these kind of more advanced things. So is that everybody happy? Okay. So I wanted to then switch now. So what's my time? 10 minutes? Okay. Great. So this I might do. I'm torn between doing it. I'm going to skip through all these slides. I didn't get to rearrange things. Sorry. Sorry. So this part I could either do I might just do on the board, but okay. So what I wanted to get to is this sort of general purpose statistical model that applies certainly for particle physics, but also applies very well to a lot of astrophysics, especially when you're doing template analyses. So all the stuff with the dark matter signal from the galactic center and all sorts of different things where you stack templates on top of each other. It's going to apply there as well. So, okay, I guess I'll just do the slides for now. Okay, unless you have a vote, slides, board. Okay, so. Okay, so I'm gonna sort of go from start at one point, and we're just going to keep adding little pieces to it. Okay, so my starting point I think is going to be the simplest kind of analysis that you can do in a particle physics experiment is just count events, right? So in that scenario, like we talked about before, there's background only or signal plus background or something, and I'm counting events, right? So when I count events, I have a Poisson distribution of the number of events that I observe given some expected number of events nu. Okay. Now, so that's my starting point. Okay, and then what do I want to say? The nu is this is an expected number of events. I can either think of it as its own parameter, or I can think of it as a function of stuff that has to do with my theory, right? So I can instead of just thinking of it its own parameter, I can think of it as a prediction that comes from my theory. So now nu is going to be nu as a function of theta. Okay, so this is just a deterministic function of the parameters of my theory. Okay, so if the mass of the Higgs is something, and the higher dimensional coefficients of some dimension 6 operators have certain values, I can predict how many events I would see. And this is also including, say, the background contributions, right? Okay, so this is all the events I expect to see, and this is some deterministic function of the parameters of my theory. And then theta here might also include things that have to do with my detector simulation, like trigger efficiencies, calibration constants, all sorts of stuff, okay? And once I specify all those things, I can predict the number of events, okay? Now, a lot of times you also have a distribution for some observable quantity x, right? So we can think about suggestively a curve that looks like this with a bump on it that hits at 750 of some arbitrary unit. You could think of something like this, right? And so I have data points. Usually you draw pictures that look like this that's kind of bent, but really there's just a bunch of data points happening along here, right? So now we're going to think of the data. I'm going to have some data xi with I equals 1 to n, right? Yeah. So this is all in here. So we'll go through it. Yeah. So this is the. Oh no. Yeah. Okay. It doesn't have 750 in it. So in this case, we also have shape information, right? So I want to include the shape information. This would be like the templates. You can just imagine these are two-dimensional, like x could be two-dimensional, right ascension and declination on the sky or something, and you have, and this is like the galactic, templates for the profiles of like, gamma ray emissions or something like that. Now, so I need to include that. So to do that, I'm going to have a product from I equals 1 to n of whatever the distribution of whatever this distribution looks like, right? Is this so? And then and that distribution might also depend on the parameters of my theory. Does this make sense? So f of x given theta is this curve that I'm drawing, but sort of normalized. So this is f of x given theta is this curve, and you can imagine that here that theta, one of the thetas can be the cross section for this bump, right? So if as you change that parameter, it might go to 0, or if I change that parameter, it might go up, or one of the parameters might be the mass of the particle that shifts it back and forth. Something that's fine, but the f of x is the total thing. So this is kind of just to guide the eye. Yep.
So f is a take from experiment.
No, that's your prediction. Yeah. And so the and the way that I'm doing it, you also need the integral of f of x given theta dx to equal 1 because it's a probability density function. Okay, so this is like the you have the it's 1 over sigma differential cross section with respect to x. Okay, so is this fine? One thing that's kind of interesting about this is that the normalization condition of this thing, right? So before I had this piece, I just sum from n equals 0 to infinity, and I get 1 for the Poisson, right? For each one of the observables, I know that it integrates to 1. But now I have this weird thing where I have both the space of the data is not like of a normal shape. It's like r to the n, and n is random, right? So what you need to do is sum over all the values of n. For each value of n, you need to have the n repeated integrals of the different x's, but each one they factorize if you think of all of the events as independent, and each one integrates to 1. So it's all 1 at the end. Okay. So this picture right here is what would if the x's are all unbend, this you would call this this part right here is an unbend likelihood. And often people talk about a unbend maximum likelihood fit, okay, which just means maximize this function with respect to theta. And when you include the Poisson term out in front, then you call it an extended unbend likelihood, or an extended unbend maximum likelihood fit, or something like that. Okay, and for what it's worth, a statistician would call this thing a marked Poisson process. Okay, so it's a Poisson process, and this thing is sort of like, where in the sky do you expect the events to happen, or where along here do you expect them to happen, and the x's are the marks. Okay, okay, but is this part fine? Yeah, yes. Yeah, so if the distribution is bend, then you can think of f as I can still like if I have a bend thing, I can still think of that as a probability distribution that's continuous in x. Oh, that's that has a continuous x that's just piecewise defined, right? And so you can use the same formalism. And then if you do that, you can see that I can break it apart into the individual bins, and then I can rewrite this whole thing as a product of a bunch of Poissons for each bin. Yeah, so here it's Poisson on the total number of counts, and then where the x's happen. Okay, if f has this form, that's piecewise continuous, then I can break it apart. I can think about each range of x, and then it's constant within each of those pieces, right? So I can think of it as like a sum of all the piecewise discontinuous pieces, and then you have a Poisson in front of each piece with some weight. Okay, and then if you do some simple mathematical whatever, you can rewrite that as a product of Poissons for each piece. There is an additional combinatoric factor about all the different ways you could partition the x's into the bins. So when you write it down at first, you don't actually see it, but it basically looks like this. It's like a multinomial times a product of Poissons. But so there's some irrelevant kind of combinatorial factor, and then a product of Poissons. It's totally equivalent. Yeah, the likelihood is exactly the same. So yeah, you can choose if it's binned, you can just write Poisson for each piece. Now, yeah. I'm sorry. Say it. You're saying there's two n's? They're the same n. They have to be the same n, right? So the I is ranging from 1 to n. It's all the data points that I have. And so for each one of them, I'm saying, what's the chance it came, that the value of x was whatever it was. So you have a product of all of those. This is assuming that all the events are independent and identically distributed, which in particle physics experiments is usually a good assumption. And then separately, there's the Poisson probability that you got that many events in. So it's the same n. Yeah.
I was saying that for a piecewise linear f, the two things are exactly two likelihoods, the second likelihood being the product of.
Yeah. You get this combinatorial factor. If you just if you do it for two bins, with a different factor, you can work it out. And there's this combinatorial factor that's there. So a lot of times you see it rewritten as a if you want this thing right here, because it has to still be normalized to 1. This is called a multinomial distribution. It's like a binomial distribution where you say probability of success or failure, but now it's a probability for each bin. So this thing is a multinomial. So a Poisson times a multinomial looks like a bunch of Poissons. So
losing some information, you just have one bin, for instance, and compare it with the extended likelihood for that.
It's the same.
But the extended likelihood thing, you would set it with all your events out one side.
Not if it's a flat bin. You don't know about it. If all your events are on one side of the bin, you're always evaluating.
In the bin case, but you know about the extended likelihood.
Yeah. The extended part is just counting, and then it's the shape. So yeah. So if you don't have shape information, you can just drop this piece or set this equal to 1 or something. But what's nice about the thing that I'm trying to get at here is we're gonna flesh it out a little bit more, but it's gonna be one formula that has a bunch of special cases, and those special cases include binned likelihoods, unbinned likelihoods, counting experiments, multi-channel counting experiments, and they'll all fit into the same formalism. Okay, all right. So great. So now let me try to go a little bit further. All right, before I do that, there's one really important piece here. Is let's say that if we were in a situation like this, sorry to do erasing, where I have all of my parameters get broken up into two parts: ones that change the shape of the distribution, and ones that or I could keep, sorry, for your notes, I'll keep it here. So I'll call it theta, shape, or sorry, theta for the counts, okay, and then theta for the shape, okay, and all of my thetas look like, get partitioned into theta for the count and theta for the shape, okay. If you're in a situation like that where the parameters factorize and the parameters theta shape only affect this piece and theta count only affect this piece, then there's no tension in the fit between those two pieces. And what happens is the likelihood totally factorizes, and this will just figure out whatever matches the number of events, and this will fit the shape. Okay, and if one of the values of theta c, are such that nu of theta c equal n, then it's just, it fits exactly, right? So the simplest thing is I don't think of it, I just have a parameter which is the total number of events. So in this language, if this just equaled theta c and I only have one parameter, right? So it's just one of my parameters is just the number of events, then the best fit value of theta c is just going to be n, and that's kind of a relevant piece of information, and then all of the fit is just fitting the shape. However, so if you were in a fit like this, say, let's imagine the data looked, like this, then if your likelihood, factorizes like that, one piece is just going to find what the right mass is, and then the other one's going to fit the height of the bump, and they're going to be totally separate from each other, right? However, if you're in a situation like the Higgs, where as a function of the mass of the Higgs boson, you also have a prediction for the cross-section of the Higgs boson, then it doesn't factorize this way, right? So that's this more general thing that I wrote, nu of theta, and this is just f of theta, and they can have shared dependence. And in that case, imagine that you go through in the process of doing the fit, the best fit mass doesn't have as many events as you would have expected, right? The fit would want to pull to a higher mass where you have fewer events, and then to account for the fact that there are the number of events. But the distribution wants to pull back the other way on the mass information, right? So if you can have tension in the fit, and if you were in that situation, you would want to know like what's the right way to weight those two effects, and this is the proper way to include those two effects. Okay, so this will encode the right way for these two things to pull on each other. And this was, there's a lot of discussion about this when we were doing like Higgs coupling measurements and things afterwards. It's like when you want to do the mass measurement of the Higgs, do we include the fact that we know the cross section for the Higgs? We could, but it assumes that it's the standard model Higgs, right? So a lot of times we would sort of change the likelihood, not take into account that we know the cross section as a function of the mass. And now what theory are we testing? it's not really it's not a quantum field theory, or at least not, we don't know which one it is. Maybe you could think of it as like some Higgs portal or something. But like but that happens a lot. That you sort of have the structure from your theory, and then you just kind of go in and monkey around with the likelihood function to like break certain kinds of relationships that the theory would have in it, because you don't want to. And you can do it, but a lot of times people would be mad because it's too model dependent, right? And unfortunately, there's for every one of those choices, they grow combinatorially, and so there's all these different options about how to do the fits and things like that, and it becomes messy very quickly. Okay, yeah.
So the n here will be the number of counts for the entire experiment, whatever that is.
Yeah, that's right. Yeah, so x's this is the data, which has n observations, and there's an x value for each one. Okay.
You said that that's the right way to do it. What do you mean exactly? Right?
Okay. Well, yeah, exactly. I mean, this is this is the actual likelihood. Like for instance, if I were when I generate example events of x, this is the function that I'm sampling. This is the statistical model. So this is, if for observed x's, this is the likelihood. So I could consider other functions that would not, and so I guess I mean right in the sense that this is the likelihood, and it has all the nice properties that you get from likelihood-based inference. So in the limit that there are a lot of observations, all your parameter estimates are going to be unbiased. They're all going to hit the minimum variance bound, and those are those results. Okay, yeah. Okay, so now let me just extend this a little bit more. I know that we're kind of at the limit of time. Is that, of course, usually you don't just have one data set. You could also have something that might look like right, which is my hand drawing of the 4-lepton distribution, right? So this is like mass of the z, twice the mass of the z, 125, and this could be M4 lepton, right? And then I have data points on this thing too. The data shouldn't have error bars on it, but that's a different discussion. Okay, so so you have some other piece of information. This is also testing the same theory, right? For this plot, I could write the same equation, right? I mean the same. Well, you're going to have a different f, and a different number of events and all these kinds of things, but it has the same form, right? So if I think of these as sometimes you refer to them as channels or categories of events or something like that, then I can just put a subscript C on everything. So I have a in C for, this is C equals 1, and this is C equals 2, category 1, category 2. So I have the number of events in category 1, the prediction for the number of events in category 1. I'm going to take advantage of my eye looking like a C. Then I have the values of the observations in categories 1 and 2. So XC is like, this is M gamma gamma, and this is M4 lepton. And then I have the, an I that runs over both of them. And then I just do a big product. Let me erase some of this. I have now a product of C, equals 1 to the number of channels or number of categories of events, right? And then of this whole big thing, right? So this is what's called a simultaneous fit, okay? So you're simultaneously trying to fit these two distributions, but with one shared set of parameters, okay? And some subset of these parameters might only affect this plot, and some subset of these parameters will only affect this plot. Some set of parameters might be, for instance, the calibration of my electromagnetic calorimeter, which affect both the gamma gamma and my 4 electron events, right? So some might be shared that way. And of course, the mass of the Higgs is going to be shared between the two, things like that, right? This way you can share different pieces of information in the simultaneous fit. And then there's another part here, which is that let's say, oftentimes I might have, say, some uncertainty about, like, you can kind of draw a dotted line here and consider this like the background part and the signal part, right? I might want to, and under here there might be some reducible background, right, that comes from things faking leptons, right? What I could do is I could choose an assignment of the charges or something that's not 0, when the sum of the charges is not 0, so I know that there can't be any Higgses there or any Z bosons or ZZ or something like that, or like choose some flavor combination that kills all of the signal and something, and then I have another distribution that just has this stuff that's faking leptons, right? So and that process might be highly uncertain, right? I don't know what processes are giving, rise to these fake leptons and noise and crap in my experiment. So as an experimentalist, if I can come up with something that I believe has the same distribution here as here, right? And this is coming from the data, then this is a data-driven background, right? So this is now just another one of these components, right? I just add another category into my fit, which is some observation that doesn't have any signal in it. And what I can use is now the observation here will help constrain this component in this part of the likelihood. Okay, and so this is oftentimes how we try to control systematic effects with these, quote, data-driven background techniques. But it just fits into the same model here.
So this be a start there.
Yeah, so the simplest thing, like this one is all one analysis. If I want, I could have imagined just breaking it up into different pieces and called this the signal region and those the sideband regions, and they would have been different categories. But it's going to all be, in this example, the likelihood that you get from these 3 partitions is the same as just thinking of it all together. Yeah, so a sideband analysis is one type of data-driven background. Yeah, so maybe I'll just mention one last one that's just a special case because it's a very important one, is that and then I'll stop, is that let's say what do I want to do? Sorry, yeah, I'll draw the sideband case just to make it easy. Okay, so let's imagine that I have this falling background and then a bump on it, right? And I think of it as sideband regions and a signal region. And now, in this case, let's say I don't use the shape information. I'm just going to count events. Okay, so here I'm going to have, let's imagine the number of events here is n. Okay, and I'll call them, there's new S events from the signal and new B events from the background. Okay, and then I have a sideband region over here. I'll consider both of them together, and we'll say that there are M events in the sideband region that's observed. Okay, And so, if you want, there's data points here or something, Okay, so, but now how many events do I expect in the sideband region? It's some other number, but the reason you would do this, and the reason it's convenient, is if you can relate those two and say that the number of events that I expect in this shaded region here is nu b, the same as the background here, times some factor tau, which is just the ratio of how many background events are here to there, right? So if I know what tau is, then that's great, right? So what is the statistical model for this case? We're going to use that formula. I'm going to have two categories, the sideband category and the signal category, right? And so it's going to look like Poisson of n given new signal plus new background times the Poisson probability for m given tau times new background, right? You see what I mean? It's just the two Poisson pieces, and there's no shape information because I'm just counting. So it's just that, okay? And there I wrote the new c of theta. Like my thetas are these two parameters, okay? So I could have called them theta s and theta b or something, but okay. So if you do this whole thing, this is the probability of n and m given nu s and nu b. And tau is a fixed known constant in this case, okay? So in this setup, nu s is the thing that I'm curious about, right? I want to know, is there some signal there, right? I want to either try to make a discovery or I want to put an upper limit on the signal rate. And the setup here is that new background is the unknown background, okay? But my sideband, it's a parameter of my theory. The background rate is a free parameter in this case, and I'm letting the data decide. But a lot of times what people would have done is not write the joint likelihood. Instead, they would have looked at the sideband measurements first, right? And they would have fit it. And they would have said, well, if you just thought of this, if you thought of it as a two-step procedure, the first thing that you would do is you'd say that new background hat equals m over tau. This would be the two-step procedure. First, I use a sideband. I get an estimate of the background. And then I go in step two, look in the signal region. And now I have an estimate of the background that I can use. But I need to propagate my uncertainty, right? And so then the propagation of uncertainty is kind of a little bit awkward. Okay, now I have to figure out how to propagate uncertainty, right? And we can talk about that. But a much nicer way to do it is not do it in two steps, is just to do it in one step. Just think of the likelihood of both of the pieces simultaneously. And then, and stuff that we'll talk about later on, this thing is what's going to be called a parameter of interest, and this is going to be called a nuisance parameter. Okay, this is I don't care what the background rate is, but I'm uncertain about it, so it's a nuisance, and it's a parameter. So it's a nuisance parameter, and I need to figure out how to make statements about the signal, the parameter of interest, when I have nuisance parameters, and we'll talk about that in the next lecture. Great, thank you.
Okay, so I asked Scott and the discussion when you come back up here, and let's start with Scott up here and the baseball go. And let's divide okay. If you were born in January and June here, you were born half the year. Weirder things next week.
Hi.
If I caught the leg off or not.
If you got what?
The leg off.
Oh, yeah, sorry. I should have given you some more warning, yeah.
Totally got it.
Oh, yeah, that would have been good. That's too bad. Well, at least.